Hello, listeners. Welcome to Duff. This is episode number 94. We're coming from The Hague. My name is Vijay. With me in today's panel is Mr. Ray from Belgium.
Mr. Ray.
Wouter from Belgium. Mr. Aurelien from somewhere in Lyon, I think.
Yeah.
Sorry. And Mr. Albin, who just moved to Switzerland. Let's start the episode, shall we? With some music.
All right.
There you go.
That's perfect. What a pro.
Exactly. It's like Walter Cronkite level shit. Sorry. Welcome to Defen, guys. So let's just dive deep into our guest today. I think this is the first time we're having 3 guests at the same time.
Yeah, I'm not quite sure about that actually. I think we've had a 5-way
Threesome,
before.
that's what you were going to say.
Yeah. Well,
I don't listen to the shit, so I don't know.
I've been banging and screwing all day, so having a threesome this evening would have been fine, you know.
This became a technical orgy.
That's the new subtext for the episode. I like it.
Exactly. Yeah. I think this is the episode will finally be cancelled. We've been waiting for this since episode 1. Cannot stop the progress.
Should we say what we're here for, VJ? What is the
Totally.
What's motivated this shit show?
I mean, it's specific. I don't want to call any of the episodes that guests are as a shit show.
Oh no,
there were a couple of shit shows in the beginning when it was only Ray and I, but now it's way more professional now.
Well, I was calling it a shit show so far because it's mostly just been you and me. So
That's true.
It's probably going to give you a lot better soon.
Yes. So keep listening. Maybe we should do a quick welcome to our guests. First of all, the oldest guest, Wouter. Well, not by age. I mean, oldest as
I think
chronologically oldest
age.
in there.
Looks like he's probably older than those guys. I mean, those guys look like they're still at school. What the fuck is going on here? You know, they're like coppers. You know, like police officers. They're getting younger and younger. These developers. You know?
Well.
Nothing to do with me. Nothing to do with me.
No, I mean, for some context. So both me and Aurelien and Albin, we work at Exoscale. It's a European cloud provider. We use a lot of Clojure, and we recently, or we're about to, depending on how you look at it, we're about to ship like a major achievement in my book. So because we've built block storage from scratch. Both of these guys and the rest of the team have been instrumental in building it, and I thought it would be nice to, talk about it, because I think it's been an amazing 2 years to build it, but also the result has far exceeded my expectations, and so I thought it might be nice to talk a bit about what we've built, how we've built it. What we wanted to do, and I absolutely wanted to put both of these guys in the spotlights because they've delivered far and beyond, in my opinion. So
what's your role in the project, Wouter, and what are these? Maybe we can have an introduction about what you do and what they do.
Yeah, so I'm the team lead for the team that's doing all the storage related things. So historically, that was the storage layer for our S3 offering, and now that's also a block storage offering. And Aurelien and Albin work in my team. So basically, I do paperwork, and they actually made the system running, sort of. So
you're just asking, are we there yet?
Kind of.
Why is it taking so long?
Why isn't this done yet? We're 2 years in, man. No, I'll let them introduce themselves as well, maybe.
Yeah.
So,
who wants to start, Albin?
Okay, so we're going for the youngest one.
It's alphabetical order, actually.
Yeah.
Yeah, the W was clearly the first one.
Yes. Reverse alphabetical order.
Oh, hang on.
No,
Doesn't
not
matter.
even that.
It's like a circular one. So I think it's like overflow, right? We have reached Wouter. Now we are going to go back to the beginning. Now. It's integer overflow.
Yep. So on my side, I've been mostly interested on distributed systems and correctness of systems. I started at Exascale working on verification of properties inside of the S3 offering. So checking that if some parts of the system crash, if we lose some parts of the system, we keep the durability and all of that guarantees. And at the same time, I did check the API correctness against some models to verify that we were to detect the parts where we had issues and confirm that the rest of the system was correctly working. And after that, so this was my end of studies internship. And afterward, I moved as a full-time engineer, just working on the distributed storage systems, mostly like the backend of the object storage and all of the block storage related stuff.
So they made you put your money where your mouth was.
Absolutely.
Nice. And what about you, Aurelien? What is your backstory?
We can't hear you, Wouter,
Oh, sorry.
if you try to say something.
Yeah, I was going to say we made him write the bugs that he used to discover.
Exactly. And it's way funnier to write bugs.
So for me, I've been working at Exascale for the past 2 years. Previously, I used to work for a small company that was doing embedded system, and I came at Exascale to work on low-level stuff, which is our storage backend and the various fleet of daemons that store data and ensure that we don't lose it. And that's it. So far, it has been mostly successful.
Are demons called a fleet, or are they called, a hellscape?
Yeah, it depends
A cohort
on
of
what you're.
Anyway, carry on.
Yeah, and that's it. We've been working on block storage for almost the past 2 years now, and yeah, we are, I think, all happy that it's coming to an end and it will be viable for our customers.
It's really nice. I think maybe it's a good idea to explain like what block storage is and what are the challenges in building this, right? It's not just okay, there is some disk space available somewhere that you can use. It's not just like that. I suppose I don't have much knowledge, but it'll be nice to have like a good idea about what was the problem that you're trying to solve, and then what is the offering, and then how you're building this one. What were the biggest challenges here?
Well, go ahead, Aurelien.
Yeah. So at Exascale, our first storage offering was an S3 compatible product. Object storage, so it stores, you can put files via an HTTP API that we will store, and we will ensure that you can retrieve them down the line. That plus a handful of properties around access control and stuff.
Mm-hmm.
So fundamentally, block storage isn't that different. The API is different because it just acts as a disk on your machine, but you will write data on it, and we will need to ensure that you can retrieve it down the line. So we've used this closeness of problem to reuse some of our software. And the major difference was that while you can accept that your object storage has a dozen of milliseconds of latency to get or write a file, you can't accept that for block storage. Like, you need it to be fast. Fast like a disk or close enough to a disk. And that was the major difficulty that we needed to face. We needed to write a system that was good enough so that that can be approximated as a disk and not as a web API.
Yeah.
So does this use like the Unix or the POSIX, like System 5 compatible, create, open, read, all these kind of things?
So we go at the lower level. What block storage is that we just present an array of blocks So you can, and the only operation you can do is you can read or write a range of bytes. So it's the same interface than a disk offers, not the interface that a file system offers.
Okay, so
more at the hardware level.
Yeah, you put file systems on top of your API then.
Yes,
okay.
Exactly.
So it's a network attachable block device, right? Like it's
right. Okay.
It's a pure disk. It has a disk-based API, so you write bytes at a certain offset on the disk, and you flush them out, and then like the operating system typically puts. I mean, you typically put the file system over the top, and then your operating system uses that, but you don't have to. So it's a very low level. We simulate a raw disk essentially, but it's network attachable.
So is it actually linked to the operating system, or is it a pure is it a pure synthesis in your like user space? So the kernel doesn't know anything about it.
No, you connect directly. On our side, we do connect the block device directly to a virtual machine, and on the customer side, it's just that a disk appeared, and you can use it. But for the customer, they can't even do the difference between a local disk and a network attached one.
So is it conceptually similar to EBS on AWS?
That's exactly the equivalent product.
Okay.
Yeah, so I was going to say the object storage is S3, the block storage is EBS.
Yeah. Okay.
So the idea is that you can basically, as the need arises, you can extend the storage that's available.
Yes, we have two constraints. The first is that on physical hypervisors, we have a limited disk space that we can allow for virtual machines. And so if a customer is creating a virtual machine which is a given size, we are going to limit the size of the disk to keep our usage ratio between like CPU, RAM, and disk. So this is why we had constraint on that level. And so the purpose of the block storage is to allow customers to go past that limit and to be like, okay, I want a small VM, but a very large disk. And on our side, we don't have the constraint of the physical disk space anymore. And there is a second big user that we're going to have. It's all of the Kubernetes stuff, where you need to have, I forgot the name, it's a PVC, but it means...
Persistent volume claim.
Yeah, you need to, for Kubernetes, if you want to have some storage with your pod, you want to attach a physical disk and then use it inside of your pod, but you don't want the pod to be linked to a single node, and you want that flexibility. And so that's the thing we are trying to solve also, and to offer something easier to use directly.
So essentially, when you attach this to a VM, it just looks like a hard drive or a disk drive. Yeah. But how do you get the storage classes then? Because as probably know, EBS has different storage classes, right? And it's like, oh, do you want to have like a spinning disk or high IOPS or SSD type of performance from this one? I'm assuming underlying technology might not be SSD or might be SSD, but you're creating some performance characteristics into different storage classes, right?
So at Exascale, we don't have a notion of storage class. We have only one offering.
Yeah.
But if we were to create a different one, it might just be a different limit that will apply to your virtual machine. Like you will get the performance that looks like an HDD or the performance that looks like an SSD.
Yeah.
And it's just an artificial limit that will be applied to.
Yeah.
But when to that point, I mean, because I think they have like guaranteed IOPS rate and this kind of stuff.
Yeah.
You know, is that something which you like? You say, okay, our offering gives us a guaranteed IOPS of whatever it is.
Exactly. We limit the number of IOPS to a number that is lower than what our system can support to ensure that you have some guarantee to hit it, and that it's fair for all of our customers.
Okay. So what is the backend then? Well, backend as in what is the behind the scenes then? I understand the interface, like how it is being used the quote unquote front end, which is the VM and CPUs, but where is actually the data going then? Somebody's computer.
Yeah, basically. No,
the cloud
is
the cloud, obviously. I mean, no, I was actually going to say like the trick with all storage systems is not necessarily, the happy path is easy. The client side API, like we're using the NBD protocol to expose the disk to the hypervisor. And like the protocol has 5 methods, I think. It's read, write, flush,
yeah,
write.
that's it. Just 3.
Yeah, I mean, and then there's like 2 which we haven't actually implemented, and that that's all of the protocol. So like that in and of itself is like super simple. The tricky part is all the error handling, right? Like what if this goes wrong? What if that goes wrong? What if we can't retrieve this? What if so that's where like all the funny stuff comes from, because you can't lose the customer data, right?
So do you have like guaranteed replica sets and that kind of stuff?
Yes. So maybe I'll just quickly do the high level overview of like what the tiers are and how that was designed, and then like feel free to ask some questions along the way, and then I'll field those to the specifics to Albin and Aurelien, basically. But so what the way the data flows is, so your VM makes let's say a write request. The hypervisor passes this on to our daemon, which lives on the same machine, right? So that's locally. So there's a local NBD server to the hypervisor itself. And this one also has a local cache. So we write, we write the bytes into a local cache first. And then either when the cache is full or when, or on a timer, we will empty the cache and ship it off machine, which is the whole point, right? Like we want to persist somewhere else. And so this talks to, in the first place, a proxy, which is the entry point into our, storage machines. And then the proxy slices, theoretically slices the input range up into what we call blobs, although practically speaking, the NBD part never actually sends anything that's larger than the maximum blob. And so this one replicates it 3 times and writes it out to 3 machines that then store this data and reply back. And then basically the read path is the inverse, where we first have to check, is this particular data in the right cache? If it is, we serve it. If it's not, we talk to the proxy. The proxy figures out a replica that the data lives on and then ships it back. So,
and what do you do? Like, what's your sort of parity checking, all those kind of things? Because Albin was talking about some correctness measurements. How do you guarantee that the writes on all of the replicas all kind of line up?
So go ahead, Albin.
Yep. All of the data is transmitted through TCP, so we have the protection at that level. And for the data at rest, we have the protection of both the drives, because most of the modern SSDs are going to check the sectors before replaying. But we also store a checksum of each blob, which is larger than a disk sector. And we have a process which is going to periodically check and ensure that all of the data on the disk is correct. And so we're sure that if a disk is starting to fail with dead sectors, or if it's had some bit flips, we're going to detect it and re-replicate the data to ensure that we stay correct at that part.
One of the things, I mean, I know this is maybe a bit off-piste, but one of the things that I heard other people, or I've heard people talk about doing with storage is, it's probably not so, I mean, it depends on the type of things that are getting stored, but if there's like a million things that are all the same, and you've got checksums of stuff, and they're writing the same thing every time, do you basically say, we're not going to bother writing that again? We're going to sort of do some fingerprinting?
To answer simply, no, we don't do deduplication of the data on the disks. We didn't add the proof that it would be worth it to implement as of today. And like we bill for that data, so we can store it. And it's not, yes, we could optimize the pricing of the system by doing that, but we don't have a big incentive doing that. So
I'm not sure if it is actually, I don't know if it is a real thing or not. Maybe as Ray was mentioning, this might be heresy or me just understanding shit completely wrong. I remember Dropbox doing this kind of stuff to make their storage very efficient and faster as well. Because if everybody is storing deafened episodes and downloading, and then 200 different customers are saving the same data, it doesn't make, I mean, obviously it's not at the file level that you can reconstruct everything. But if there is a block that is pattern that is exactly the same, then there is no point in copying it. Yeah, sorry.
So in theory, it could be done. I think there are a few blockers that prevent us from doing that successfully. So unlike Dropbox, our customer can use the product to store a lot of different data. So Dropbox is kind of suited for a lot of files, maybe business files. So they have a likelihood of having copies of the same file that is somehow large. On our case, as we just expose a disk, our customer can use that to store anything. A database, raw videos, compressed videos. So the likelihood of finding same data at different places is getting lower. And as we also receive unstructured data, we just receive a stream of bytes. It would be difficult to try to analyze those, to try to find patterns and repetition. So it is going to cost us a significant amount of processing power to do that.
I mean, there was an interesting, I need to look this one up, long time ago. There was an interesting website or an online experiment that some artists created, that you could type any sequence of words, any sequence of letters in English, you could find that on that page. It doesn't matter what in what order or whatever. So it seems like eventually, if you have enough entropy, if you have enough space, you can just put all the bytes available in combination. That means it doesn't matter what people are going to store. I don't know. It might be petascale, whatever.
And one last thing that prevents us from doing that is that eventually, if we want to encrypt customer data, it means that we can't share the same data from different customers.
Of course, yeah. But it is an interesting space, right? It is an interesting idea. Obviously, Dropbox is, as you said, I don't think they're encrypting. I mean, they're probably encrypting only with their own key, whatever, at some location when they're doing the offsite stuff. Cool. So, yeah. Sorry, Ray, do you have any?
No, I was just going to say, so let's go back to the kind of hardware then, because, assuming that you're running SSDs, like you say, you've got all this kind of stuff and you've got it on different machines, like how you've got essentially, how much storage are you actually kind of having to provision yourself? I mean, how are you doing that? Are you kind of like saying, okay, like we've got like, I don't know, a petabyte of data that we've bought, and we're going to like, and then let's say you've got a certain amount of capacity, and how do you kind of like account for that and budget for future needs? That's kind of like an interesting challenge, I think, on the storage side, because obviously storage is not free, it turns out, despite what all these photographic bullshitters tell you, they always end up charging you for it, so that's the question really, is how do you kind of manage the kind of predictability of the storage array that you've got to have available? Because I'm guessing that if you've got some customers that will suddenly write, I don't know, a few terabytes of data, that it's like, oh shit, we've got to bring a load more disks online, and you have to really do it. You've got to screw them into a machine somewhere. So how do you cope with that kind of like that kind of scalability that the cloud kind of is meant to solve for? So how do you solve for it?
So, Albin, if you want, maybe.
Yeah, I don't know. Maybe we want a
I-
business answer from Wouter.
Oh yeah.
Because you're the manager, you're the one we should answer this one.
All right.
Yeah, but actually,
I'll do. All right. It's
the
political. I
technical
get to go.
response isn't very interesting. Like, we monitor. When it gets too high, we order more hardware, and
Like
we were in.
basically we order capacity when our cluster is 50% full. So
Right.
we vary, and it depends on how large a zone already is. Talking about object storage now, because this is the way more mature system, where we have some experience with increasing capacity for the block storage offering. This is currently in preview. It's available in one zone. There is some capacity, but like obviously it's not being used too much, and we don't really. I mean, we don't really have good heuristics yet for like, okay, this is how full we can run the system. But for the object storage one, the larger zones are several petabyte, and so these, even for these ones, I think like when we hit the 60% mark, that's like the absolute latest trigger to add additional capacity to those. As these clusters, so it's also like a size thing, if you know what I mean. Like the larger the cluster already is, the percentage at which we can order additional capacity goes up, because the chances of an individual customer basically drowning out the system go down. But like the smaller zones, like we've got a few really small zones where I think the cluster size is a few hundred terabytes. And so those are like within a realm where a single customer could theoretically walk up and like fill it up really fast.
Right.
So as always, the answer is it depends a bit, but basically
Another question for you on the sort of commercial aspects of it is, I notice when I'm buying SSDs, that there's a sort of like there's a different set of prices as you go through the sort of capacity range. There's a sort of sweet spot, at least at the consumer level. So what's it like at the kind of like warehouse, kind of business to business level? Where do you find like buying the absolute maximum amount of like SSD is what you have to do, and you just have to pay the top dollar, or do you buy medium size, like, don't call them discs, I guess, anymore. But
just go to eBay and then buy the second one.
Well, that's what I'm thinking. Or something. I mean, do you end up like buying like mid-level? What's the optimal pricing? I guess that's the question. Is like, how do you do the pricing so that you don't feel like you're like overcommitting in terms of like that extra premium that you would pay for, like, I don't know, 16 terabytes or whatever. I don't even know honestly what SSDs are these days. So, but answer that question first, maybe. What kind of like options do you have in terms of buying SSDs?
We buy machines more than SSDs, really.
But don't SSDs aren't they like? Don't you like screw them in with NVMs or whatever, or NVMEs, or is it you don't just like screw in SSDs these days? Or
I don't.
There's somebody going there
or
and then
slot them in.
Like
I mean, I do on my machine. You've got to like slot SSDs in, or you've got to screw them in via NVMe or something.
Yeah, they're
probably
NVMe
these are all
drives,
onboard
sure,
probably these days, right? With
no, like they are for the block storage. They are NVMe drives. For the object storage, they are in fact hard disks spinning metal.
Yeah.
But we tend to buy the machines as such, and so the vendor will make a proposition, and that will have there will be some choice that we have for like the SSDs or like the drives that fit, but we typically don't buy them individually. Like it's and then similarly, like we do look at like price per gigabyte and things like that. Like we don't buy the absolute max. And there's also, especially in the object storage side where it's hard drives, so these have gotten way denser, but the bandwidth of the bus hasn't gone up, right? So this means that you can still only drive X amount of data, bits or bytes per second to the same disk. So a denser drive, and like also big differences in density between drives, doesn't necessarily it doesn't work too well to like load balance the activity on the cluster. Because like the way that it sort of works is we try to spread and like maybe we can explain what that is, but like we've got an intermediate concept when we store the data like physically on the machine. So there's a concept of a partition, which think of it as a 100 gig segment of the disk basically. And this is the entity that gets replicated. So we don't replicate like individual bytes, like we replicate partitions across.
Right.
And we try to load balance the data over the individual partitions, so that we spread that evenly. And so denser disks have more active partitions on them, but that also means that the more partitions you have that are open for writing, the more bandwidth that this host is going to attract. In that sometime, I mean, we've had some issues with that. We solved them now. It's not an issue anymore. But so basically, like denser disks are useful if most of your storage is cold, where it's written once and then you can store it like forever, and it's never like you don't need to like overwrite it again and again and again. So there are like a few things, but like mostly it's like we try to look at like most bang for the buck, really.
Yeah.
In terms of
and
capacity.
do you? I mean, you're just talking there about like if you have increased partitions. Do you like have two NICs so that or several NICs so that you have like one for the sort of front facing and one for the replication?
No, it's also load balance. It's just aggregated.
All right.
So we use this networking trick called ECMP, equal cost multipathing. And so basically both NICs expose an IP that has the same routing weight. And so that kind of means that if you're sending traffic to that particular IP, then there will be like some load balancing going on, and so 50% will take the one NIC and 50% will take the other one. But the balancing is at like the TCP layer. So like one TCP connection will come in over one NIC and then the other over the other. So if you've got a sufficient amount of clients connecting, then you end up spreading the load between both of the NICs.
So you're still a believer in TCP then, rather than UDP for your storage?
Well, so good you said,
because isn't Quick going to change all that? You know.
Like benefits of TCP, like TCP comes with integrity guarantees. Turns out if you're piping data over the wire, you
just fire and forget and hope it lands.
Yeah, exactly.
What could possibly go wrong? You know,
I think this is the difference between people used to having this Control S in their muscle memory. Like you never know, Control S. So, Command S.
But we in fact. Like we actually rely on this, right? On the TCP integrity guarantees, because we used to in the past. So basically, when you said like for checksumming, like we checksum each blob, right? So each blob gets hashed, and we send the hash with the blob for integrity stuff. So in the past, when we wrote down a blob, we would immediately we would also pass. So when we wrote out the blob to disk, right? Like so, this is in our storage component, which is called blobd. And this also for the record, like this is a shared component between object and block storage. We didn't really get to tell that, but we made the decision very early on to not reinvent the storage layer and take the storage layer that we knew and have operated for 5-6 years now. I don't know. And so we decided to take that expertise and the battle testing that this system had gone through and like reuse it as the storage layer of block storage. So both of those are. So when we talk about that system, like we're actually talking about both systems. But in the past, we used to stream the bytes through a hashing function and compare the hash with what was given. But turns out that this was a compute that we didn't have to do because TCP is already doing that for you. And so that check would never fail, and we removed it and we gained some free performance. Like would so and essentially, like Quick has, and if you look at like these or HTTP3 or whatever, like they're based on UDP, but they end up re-implementing a lot of stuff that TCP gives you for free, right?
Mm-hmm.
And so that's it. And I guess there's some use cases at like super high throughput and volume and Google scale where some of the downsides from TCP are too expensive for them, and it makes sense for them to re-implement just the set they need on top of UDP. But at least at the scale we are at, we've not seen that like TCP doesn't factor in at all into the overhead that we're seeing, and we eyeball the system very closely. So like we're nowhere. I mean, I wouldn't know why we would change it out. I don't think it would make any meaningful difference. So I will have all the goodness of TCP,
So I mean, from your go on, Vijay.
Yeah. No, I was trying to maybe quick digression or maybe diversion into the title of the podcast, a bit. I'm curious about Albin and Aurelien, your programming language journey and your experience, and where did you encounter Clojure, and what is the tech stack that you're using right now to implement all this, right? I mean, if it is all C, then then nice.
What are we doing here?
We're just gonna yay, deafen now in C, and then moving on. So I'd love to know the tech stack and how it is implemented as well, right? And I think we touched different concepts, different layers. If you can give us some insight into that one, just read the code and then we'll be happy. Or this is just ChatGPT. Build this block storage system for me. Then it just tells you some shit that looks like Python but is actually SQL.
Do you want to go, Albin? Or?
If you want to start talking about NVIDIA agent and GovD, go for it, and I will talk about the proxy after.
Sure. So at Exascale, we use mostly two programming languages, Clojure and Go for the most low-level stuff. We used to write some low-level component in C in the past, but I think since the last 4 or 3 years, we've moved to Go to have easier maintainability than C, while keeping some of the nice low-level properties. So our storage engine is written in Go, as well as the agent that talks to the virtual machine manager, QEMU. And apart from these two things that are in Go, we write Clojure stuff. So the main component here in the equation would be the proxy that receives write from the NVIDIA agent and from the virtual machine, and that dispatches them to the storage engines. I was mostly working on the Go part and didn't touch a lot of Clojure up until recently. But Albin is more of an expert and can probably discuss a bit more.
But why the difference? Because if I'm assuming, proxy is also a very critical component, and then your protocol stuff as well. Why pick Clojure for proxy? And then I think Go is a bit clearer for me. Sorry, go ahead.
The objective was to reuse some of the components we already had inside of the object storage, mostly the part which is able to stream data to the storage layer. That part was already battle tested, and we knew how to operate it, and we already had all of the visibility, the tracing, the alerting required on that part. And we also decided to use the same metadata layer, but in a different way. And we already knew how to interact with it, even if we did drift a lot from the implementation inside of the block storage. But we were more confident in using Clojure at that level because we knew how to interact with other components.
And so generally speaking, like the heuristic is like low level side effecty stuff tends to be done in Go. So this is most of the agents that we have, because essentially, like if we have to run a JVM, that's one, close to a gig of memory that's just not coming back. And so if we have to do that for pretty much every agent on a hypervisor, we're going to consume quite a bit of memory that we can't sell to customers. And then similarly, historically, so blobd runs on, for the object storage, extremely low powered boxes. And they just did not have the hardware profile to run a JVM at the speeds that we needed. And so Go makes sense there. And then we try to use Clojure for anything that has to implement some form of business logic. So once it's more than just straight up side effect, because like blobd, essentially the job of blobd is take some bytes, write them to disk, and then error handling. That's 90% of the stuff. And so for the NBD agent, it's fairly similar. Sorry. The proxy tends to, this tends to have some more logic involved, right? Because this is the index which maps offsets on a disk to blobs on an actual, offsets on a volume on blobs on bytes on an actual disk somewhere. So that tends to have some more business logic. Now for block storage, that's again fairly limited because of the space. But in object storage, if you've ever looked at all the options that S3 exposes, there's quite a lot of bells and whistles. So that's kind of the heuristic that we try to use. And so given the history with object storage, and again like the problem space of each of the individual components, that's where we landed up. Ray asked a question about the garbage collection. So again, we when we rewrote blobd from C to Go, we heavily benchmarked this, and so clearly GC has a bit of overhead, but not enough to actually matter. So it was fine.
GC on Go is different than JVM type thing, right?
Yeah, it doesn't stop the world for 2 minutes straight.
Yeah, exactly. That's what I mean. There's no lock and sweep or whatever the shit that JVM does these days.
That said, so because you mentioned it on our block storage proxy, which is clearly latency sensitive, right? It can't go on a vacation for 2 minutes because that's a read that's not returning data for 2 minutes. So we're using this new, relatively new algorithm on the JVM called what's it? ZGC, I think.
Yes.
Which guarantees, like, it makes a different trade-off to traditional GC. So traditional GC, basically when you overload the memory allocation, like the GC pauses will become longer. What ZGC does is it guarantees that your GC is sub-millisecond, but it will slow down allocations. So whenever you request new piece of memory, and it notices that it's getting, up to its maximum allowed time for garbage collection, it will basically slow you down and just return from those calls slower and slower. So your application still slows down if you overload the memory that you request, but it tends to be more graceful. So
a quick question about that. It's like one of the things that the Java, like the low latency Java folks did, was they used these ring buffers, So the fundamental idea of a ring buffer is essentially that you allocate some memory and then you basically reuse that memory that you allocate, which is a kind of like an age-old trick, from like C and all these other kind of like low-level languages as well. And they brought that up to Java. And I'm guessing that you're writing these blobs. So isn't it possible for you just to like say, okay, well, we're just going to allocate a whole bunch of memory for these blobs? Those are the things that get GC'd. So fuck that. We'll just keep a memory and have a ring buffer that we just write into. Maybe as you thought about that, I don't know.
Yeah, so it would be a very valid strategy that would work, but it turns out that the Go GC is actually performant enough that you can write stuff without caring, and it's good enough for a long while.
Yeah.
But we do still play a few tricks like this one to not allocate for some object or for some memory. That way we reduce the overall pressure on the GC and the overall work that it needs to do. But we only do that for critical stuff. And for the general coding, we just use the GC, we allocate, and it's fine.
But both of you, did you start with Clojure or Go or C, or what was your first language, or JavaScript, for fuck's sake?
So mine was, I come from the embedded world. My studies were on embedded system. So I was doing C and then Go.
Okay.
And then a
So
bit
you've
of
never been
stuff.
corrupted by JavaScript?
No, not JavaScript.
Not yet.
I mean, yeah. In my previous job, I had to write a JavaScript engine in Go, or at least wire something that executes JavaScript in Go, but I don't know if it's current.
And for you, Albin?
If I remember correctly, the first language that I really learned was OCaml, but then I quickly switched to C.
Wow. Why?
This was the path we had in my school.
Oh, right. Okay.
We were starting with OCaml for the algorithm.
Yeah.
And then we went to C to get the how a system works view.
Don't you have this kind of a general affinity around some countries using some language? I heard a few people from France learning OCaml. I think there is also another language called Opa or something that also came from some French folks, I think, at some point. Which literally means grandfather in Dutch. It's interesting. But,
well, Prolog as well, they're just...
yeah. I think there is is it like, because if you write OCaml, everything is in the other way, like French people speak, like color, do, whatever, fuck, like everything is there. In French, I need to say color of something, or what is it, like a...
It doesn't strike me as a specific feature of OCaml.
I don't know any OCaml, so I can be an expert in this.
It's just, don't worry.
I guess, like,
it's like an old man ranting to the wind. Don't worry about it.
Exactly. Yeah.
But like OCaml was invented and is still being developed by a French university. It's like if you're studying in Lausanne in the EPFL, you're going to learn Scala because it's it was invented there, and
not anymore, I suppose, but yeah.
There is some affinity coming from there.
Yeah. It is an interesting view, right? Like there are I know GHC, for example, the Haskell compiler was from Glasgow, and then there's a bit of Haskell stuff there, and Utrecht University has another Haskell compiler for themselves, and then I heard more Haskell programmers in Netherlands than any other country, and I think in India, I think we just learn whatever the thing that is going to get us.
So we're arriving at the conclusion. So we're arriving at the conclusion that the French are chauvinist.
Yeah, for sure.
Oh my God!
There's no debate on that.
But Albin, coming back to your journey, I mean, let's say you did OCaml and you did C at school, but then like you said this was your first job after you got an internship, so I guess you were were you doing Go or Clojure? Was that your next after the C?
Well, I did learn other languages in school, but when I came to Exascale, I never did any Golang or any Clojure. And so the first thing I did was testing the Golang program, BlobD, with using Jepsen, which is in Clojure.
Yeah.
So I started learning those two languages at the same time. And when I was able to find a bug, I was going inside of the Go code to understand it, and then going back to Clojure, and this is how I did learn those.
That was going to be my next question, because you're working on distributed systems. Did you Jepsen it, and then what are the results?
Yeah, it's mostly Jepsen, and which we didn't use a lot on the block storage because it's quite complex to plug in, and the logic inside of Jepsen to create a new system and to test it, it's very easy to test a single component, which is the same thing on all of the systems and interact with them. But when you start to have a system where you have multiple different components that interact together, it's slightly more complex to orchestrate correctly.
Yeah. I think mostly I see all the distributed database systems generally, that those are much more easier to test with Jepsen, I think.
Maybe not super easier, but at least
There's probably a reason they all pay King Kingsbury.
Yeah,
whatever. He's a king, but
but
it's probably a reason they pay him quite a bit to do the tests. I mean, it's amazing software. We found bugs with it, so it's absolutely great. But it's not a plug-and-play test framework. Let's put it like that.
I mean, it's testing distributed systems, right? I mean, the systems themselves are fairly complicated already. That means if you want to test them, that means the scenarios that you need to look up and then design, and every system is built differently. So you need to figure out how to. It's not just there is an iOS application, go and test it. Click the buttons, and it's not that easy.
Maybe another question, since you're recently coming out of academia, is whether you were given training in formal techniques like COC or TLA plus.
I didn't add anything on that topic.
Oh, okay. Were you aware of those things, or is that not something?
Yes, when I started searching on that field, I started with the formal approach, but it was not very conclusive because the system is very simple in the design. Like, it's a immutable key value store. So for a given key, we will only write a single value and we will never write anything else. And so all of the bugs were in the implementation, not in the design. So the formal view was not the best approach for that.
Probably the specification wise, it's pretty simple, I guess. The system is simple, as in there is not many code paths or not many things that you need to test.
If we take just the storage backend, it's super simple and you will not learn anything by doing some formal test. If you take the object storage front end, it's way too complex to model everything. So you're out of luck on this one. Maybe on the block storage, we might have been able to model that, but you still end up on the page where you are going to model something and the implementation is different and you're going to miss something. So might be a very good way to do models when you have very large teams and you want to have a state of the world between components when they exchange, and to check the state of the entire system in itself. But we are at a scale a bit too small to be able to leverage those techniques.
Maybe the other question I've got for you is then, it's like, typically with Go, you're looking at very, you like Aurelien said, it's like very high performance systems, and Clojure is usually good enough performance, but it's not like super high performance. The predictability of it, obviously Java and Clojure can go fast, if you use certain tricks or make sure you do profiling or whatever. I'm not going to say you can't make it like that, but I'm guessing the way you're doing it, you're talking about like having a Clojure proxy going over a network. So do you find like that it's like, how do you guarantee the performance of this system? Because if you're saying you got to write to disk, and you're going to give the same performance as writing to disk, that does strike me as slightly odd if you've got Clojure in the middle there, because that seems like a bit of a risk for performance.
Currently, the proxy is able to process a read or a write in 1.4, 1.5 milliseconds, and which is good enough to operate the system and to deliver the volume of IOPS we promise.
And one thing to take in mind, that given that the proxy is written in Clojure, it means that we can scale, just give it more CPU, just create one more instance, which is unlike for our Go agent where we just want to drive the whole disk at maximum performance. So as long as the latency of our Clojure application are good enough, even if it consumes a bit too much CPU or memory, that's an acceptable trade-off for us.
But it sounds like it's good enough anyway, regardless, actually.
Yeah. And we've measured, and it's fine.
We
had doubt that
benchmark
the Clojure proxy could deliver this performance, but it turns out it can.
We at some point did write a reasonably complete Go version of the proxy as well, and it, was performing within, the same order of magnitude.
So it's not worth the maintenance cost, basically.
No, in fact, it was slower. Basically, it was slower than the Clojure one. Clearly, the Clojure one had been optimized. I mean, had seen some optimizations at that point, and the Go version was, we spent some time on it as well, but luckily it had not received the same amount of detailed analysis as we had done on the Clojure version. But
I'm guessing the Clojure one uses some sort of underlying Java library or IO library, or is that not correct, like Netty or something?
Yes. Actually, we rely on what's it from Zach? Aleph.
Oh, Aleph, okay. Aleph uses Netty, I think, underneath, doesn't it?
Yeah, actually, no. For block storage, there's no Aleph because we use gRPC. But yeah, it's Netty underneath still. But yeah. So obviously, there's some interop and there's some, but we did compare, and so basically, when we tune it, the Clojure ended up, or basically the JVM ends up being as fast as Go, and then the benefits of something like Clojure in the proxy way up, right? Because it is a nice language to, it's a nice language to experiment with, and it's a nice language to do data reshaping with as well, right? If you need to turn things around. So clearly, if all you're doing is just piping, the core function of the system is still piping bytes through, but the function of the proxy is to provide an index, right? Because we have this mapping of offset on your volume to blob, basically, that needs to be maintained and needs to go fast, and there's some ref counting going on to make all of that working. So there is some business logic, and it is nice to be able to express that in Clojure.
Is that what you were talking about earlier on with Albin, with the metadata stuff?
Yes. So we actually haven't touched on what that is. So maybe we should explain it a bit more. So the proxy exposes a gRPC front end, which again has a fairly straightforward API. It's write extent, read extent, basically, and then get volume metadata, because a volume has a name and a size and whatever. And so an extent is essentially a range of bytes. So it's an offset within your volume, right? Like I'm 100 bytes off the start, and it's the length, and that's an extent, essentially. So that's the primitive that we read and write. And like I said, the proxy takes that and slices this up into blobs, and then blobs are written into partitions or replicated. And so this is the thing that eventually ends up on a disk. And so the proxy's function is to, when you get a read for a specific range of bytes, we need to figure out which blob we need to go retrieve in our cluster of files or storage servers, basically. And that needs to go fast, right? Like we can't spend a whole lot of time on that, so you want that indexing operation to go really fast. And then secondly, as with most network attachable storage, we offer snapshots, so you can take a snapshot of your disk, and so this is also managed by the proxy, right? So it essentially has an index of a layered index of offset to a reference like blob ID, essentially, which is the reference to the data itself. Then. And that needs to go fast, and we do some ref counting on the blobs, because when you have snapshots, multiple snapshots, well, we do data reuse at that level, right? Like that's kind of where. So you can have multiple live extents pointing at a particular blob. So we need to ref count this. When the ref count hits 0, we can go clean up the data. And there's a few other things there as well. For functionality for promoting a snapshot into a new volume, all of that is implemented inside of Clojure. And so this ends up, all these things end up sort of looking like a reduce over a vector of bytes, basically. And that's a nice, way to model that problem. And then where I was trying to get to is for we've got a database that we eventually store that into. So we're using FoundationDB for this one. So FoundationDB basically contains our actual index of offset to blob.
So it's like your file system table where you keep all
Yes.
I mean, it's interesting that with that the concepts that apply to I think at Martin Kleppmann's book, like exploding the database and then moving it into different parts, and pretty much similar. If I hear your analogy, I mean, it's similar to if you understand how a hard disk works and then identify the components separately and move them into highly scalable systems separately. Essentially move the head to somewhere, move the disk to somewhere, move the partition table to somewhere, and then you have a scalable system essentially. I mean, I make it sound easy, but I'm sure it's way more fucking complicated than this. But it seems like similar to that kind of ideas. And
yeah, it's like all the issues with reliably storing data with the added benefit of having all distributed systems problems.
Exactly.
But
yeah.
But no, like it feels for me like it feels a bit recursive or fractal actually, where it's kind of like we expose a disk which talks to a system that kind of like you said is modeled after how a disk works, which eventually like still goes onto a disk. Like it's the same things sort of keep coming up.
It's like a huge hard drive, but then distributed into smaller hard drives.
Yes.
In the end, they're all hard drives.
I mean, you could call it virtual even, couldn't you?
Yeah, fair enough. So I got just a couple of more questions because we're almost hitting we did hit the 1 hour mark, but for Albin and Aurelien. So you come from non-Clojure stuff, and then I think mostly probably Albin and then Aurelien, by virtue of proximity, touched most of the Clojure crap as well. What is your experience been with Clojure, and how do you feel about the language and tooling? And obviously, my standard question is, which editors do you use? And maybe the final question is like, what is the next step? So it's a three-parter, right? So what do you feel about Clojure? But more importantly, what editors do you use? And then less importantly, what is the next step for you? What is the next step in this tech stack? Or for you, what are you interested in?
For my experience with Clojure, I think like it's really good at doing some equivalence of MapReduce mutations and to take something and apply mutations and at the end store it in a database, return it, do some logic at that level. And for that kind of interactions, it's very elegant. But when you're trying to model the side effect parts, sometimes when you're trying to have some performance at the same time, you're going to end up with some dirty Clojure at some point when you need to play a bit with the parallelism and the way we interact with database transactions and all of that stuff. And so when you end up with functions that are 200 lines of super compact code inside of a single transaction, it can be a bit tough to read. But I'm not a very big advocate for a given language or another. I just like, we managed to do it in Clojure.
You're on the wrong podcast for it. No?
Clojure. But like, it could be any language. Like, I'm not a huge advocate for just the language. Like, it's just a tool, and it did work. So, but I'm not strongly in favor or against it. indeed, when we start talking about editors, like I'm a Vim user, so
well, goodbye.
So
It was nice talking to you.
So initially I'm a Vim user, so I tried to use the Vim cider if I remember correctly.
Yeah.
But it was absolutely horrific, and so I didn't want it to use Emacs, so I went with Visual Studio Code. No, VS Code instead. Yeah, it's not the same thing, and it's working fine.
Fair enough. There is a reason why you moved to Switzerland.
Yeah, I'm not a huge fan of very complex macros and being able to do anything in like just using two key bindings and starting at everything. Like
Yeah.
the application is so complex to start in itself that I will have to use the REPL connect and that's it. I'm able to work.
Yeah.
But yeah, that's a very good point for Clojure. It's like when you want to run tests or stuff like that, the REPL mechanism is so useful. Like you can just go on a pre-production node and you shoot your code instantly, and you have directly you have the tracing, you have the logs, you have the metrics, you have the flame graph, which is going to work instantly, and you don't have to recompile everything locally, deploy it, and all of that stuff. So that's the part I find in the development workflow, which is really, really great on the ecosystem.
Yeah.
And like you SSH port forward, and you can just connect, and it just works.
How about you, Albin? Aurelien, how about you?
Okay, so let's start with the editor first.
So we can shut down the discussion if I get the wrong answer.
So I'm an Emacs guy.
Yes. Okay. So
oh dear.
I think now I'm gonna bribe Wouter to remove Rays and Albin's tracks completely.
So as a disclaimer, I am not a Clojure expert by all means. I've dabbled a bit with it, but there are a few things that I prefer in Go.
Yeah.
One thing about the tooling, the quality of the tooling in the Go ecosystem is very high. The ability and how to test and how it's integrated, to do profiling, to do imports and modules, it's all as coming as a single bundle where no choice is given to the user. Like you use the Go toolchain. And that I find makes for a very pleasant experience. Whereas in Clojure, I mean, I am not an expert, but at Exascale, we had to have discussion on how do we import stuff? What is our package manager? What is our way to run test? What is which differs in every project? So
bike sheds abound.
Yeah. For that, I think I like the Go's approach.
Yeah.
I also like what I also like in Go is and that is probably personal, but I find Go to be more readable than Clojure. It's probably more annoying to write because everyone knows that you need to write if air is not nil, return air
exactly.
everywhere in Go. But it has the nice property that when you read it, regardless of the person that wrote this code, you can read it fine, which I find it to be not that true in Clojure. Like, if some wizard wrote some Clojure code, there is a high probability that it's impossible to read.
It's possible. The Go blocks make Go a little bit more tricky, don't they? I mean, I've found that myself when I've written Go, that Go blocks aren't always super obvious.
Go channels.
Yeah. You mean the ability to spawn a Go routine into...
Yeah.
That definitely needs some design. Like you need to upfront sort of say like, this is my concurrency strategy, and like you need some upfront bike shedding to figure out how you're going to handle that, so that because if you just spawn random Go routines everywhere, like you're not going to be happy. I think it comes a bit with the domain as well, where explicit error handling is really nice if 90% of your code base revolves around handling errors, as it does for the storage layer. Like what if we couldn't read? What if we couldn't write? What if like the database update failed? And like what do we need to roll that back? Could like there's a like you want to explicitly consider all of those failure modes like one by one and figure out what you need to do. Do I need to write it again? Do I need to pull in something from replication? Do I need to and there's tons of scenarios, and Go having explicit error handling there makes, it's not necessarily a pretty file, but like that's the logic of the program. So it's nice that it's like all in there, and exceptions are not like exceptions lead to uglier code if you need to handle them all at the level that you sort of have to do when you're handling low level storage stuff. And so that's for me, like that's why I like Go for like these low level agents. But for example, in the proxy, there's we still care about the other errors, don't worry, but like it plays less of a role. And so because like Clojure is really nice if you just write down the happy path, right? Like if what you have is a pure function, nothing can blow up, like you get a beautiful piece of code that very elegantly expresses like your idea. The moment you throw IO in the mix and you get then it becomes a bit your code won't look as pretty anymore. Like Clojure can definitely do all that stuff, and it absolutely does all that stuff, but like some of the elegance gets lost. And so like we carefully try to balance it. I must echo Aurelien's point of like when you try to collaborate on large code bases with teams, the fact that Go has like one way to do stuff is nice, and it eliminates tons of bike shedding. Because the most beautiful piece of code you've written is your Clojure. The ugliest piece of code you've ever seen is somebody else's Clojure. Like I'm making I'm making fun of it, but there's some truth to that, right?
Certainly, yeah.
And so it's nice if like if you're doing some, if you are doing like some creative coding, like all of the interactivity is super nice, and like the audience is used, so like none of those problems play, and Clojure is perfect. If you've got four teams that need to, if not work on the same code basis, like at least be able to share idioms and common language, then you now introduced like a bunch of bike shedding that needs to happen, and it's the type of bike shedding that people tend to have strong opinions about. So so that's
that makes things way more complicated. I think in the social the social problems of coding, that those are this is one thing that I just started dabbling with Go a little bit, and I wrote more if error nil than real code so far in terms of the line count, but I can see when I was looking at the latest talks, and I think there was a talk reviewing Go's history recently, what happened with Go and whatever, and there were some social problems that were resolved, right? Otherwise it has always been like a pain in every project. Like every project has a different style, every project has a different way of doing things, every project uses, some projects are macro heavy, some projects use whatever the style that they want. On the other hand, I think it gives you way more flexibility in terms of thinking and building the code up, but not necessarily covering all the parts as you're mentioning. I'm wondering if you have written all the, at least one of the Go program, that if you write with the same level of robustness in terms of the error paths and everything, it would probably look the same in Clojure, right? Uglier, quote unquote, uglier Clojure, because you're now using all these if error nil equivalents in Clojure.
It's like try catch this exception, catch that exception, catch the other exception. Like it tends to be a bit.
I think the thing though is that like Go was written to replace C, which was like essentially to try and make a better systems programming language. It wasn't written to. I mean, people use it these days for high level things, but to me, that's like, I don't know why they do it, because to me, you end up writing a lot more lines of code and a lot more junky code than you would in something like Clojure, which is much more suitable for experimentation and, thinking about new things and innovating. Whereas Go to me is like, yeah, it's good for daemons, it's good for operating system things. It has its place, but it's too verbose in my opinion for these like more high level programming tasks.
So what I wanted to bring up was a bit. I think I'm in Albin's camp. Like languages are tools for me, and like I will use the tool that helps me get the job done. I have a soft spot for Clojure. Like it's a great tool, and it has its places. But what I wanted to point out was that the fact that Go wasn't really intended to be, the next Python, right? Like as you
exactly.
said. Yeah. But tons of people are using it in that space, and it still survives it, which I think speaks to the power of the language and the tooling. Like they hit on something that allows that makes people use it outside of the Goldilocks zone that it was designed for. And I think the other way around goes as well. Like the fact that we managed to use something Clojure for the proxy, which admittedly it was not primarily designed for. Although I do think Rich sort of first designed the language to build the database that he wanted. Like it's not. I mean, it's not entire. I mean, but basically, like it's sufficiently far outside of the comfort zone of the language. But it still works well. And so I think that speaks to the power of actually both tools. Like they're really good tools, and they manage to do more than they were potentially initially designed for. Yeah. And so but I definitely don't want this to be like, they both have their place. And what I hope is that we manage to use the right tool in the right place, basically.
Yeah.
I think it's understanding the problem and understanding the team, understanding the dynamics, and then picking the right tool essentially.
And you can build high performance systems with Clojure, and we do at Exascale, like we do. But you have to, there's trade-offs to be made everywhere, right? But I think it's it as Albin said, like it ended up working out really well. And part of that is also the context. Like we had experience using it for proxies and web servers. We had experience interacting with FoundationDB from the language. We had experience interacting with blobd from the language. So it was the natural next move to write this in Clojure as well, and it worked out super fine. And as Aurelien said, like it's also the proxy process in the sense that if we need to give it a bit more runtime power to get those development time efficiencies, then that's also fine, right? Provided we get the latency low enough. That's the one thing we care about. Like the latency for an individual request needs to be fast enough. That's it. So even if like the runtime operating profile is like a bit more memory and a bit more CPU, that's fine, because we don't have 1 million of these. We've got 6 or 8. It's okay. While on the daemon side, we've got 1,000 blobd servers at the moment, more or less. So the numbers are different.
Yeah, it makes sense.
Yeah, but like you say, I mean, if you're writing low level code, there's no way you can use Clojure for that. That just doesn't have the interaction with the operating system. It's a hosted language, so it's either going to use JavaScript or Java. And I don't think anyone in their right mind would really say that Java is a system programming language. Sure, God people have used it for it, but I know. But I think
no, it's not. You don't have unsigned types, which is painful when you have to work with bytes. No, I tend to agree, which is why we chose not to, right? So
I mean, I think the other thing that's lacking to some extent with Java, and it has been for a long time, that's one of the reasons why Clojure suffers from it as well, is there isn't a super FFI, like you guys are using TCP/IP to do it, but another way of doing it would be over FFI, but it seems like that's a big problem with the JVM and things like C and Go and other sort of low-level languages, is that the FFI is just, it's coming with Project Panama and stuff like this. They're trying to improve their FFI, mostly for things like AI and LLMs and stuff like this, and these other kind of like high-level processing things. But, doesn't seem good. Yeah. Any minute now, yes.
Yeah, we
To
took a look
be
at
fair,
it. But
the FFI in Go isn't great either. I mean, it has significant downsides. You can use it, but it's going to add complexity to your project, and it's going to cost something. Be it in
Right.
terms of usability, that the good Go tooling doesn't just work anymore. You need to bring in C tooling, and I think it's very difficult to create a good language that is both good in itself and has good FFI.
Yeah, I'm looking at Zig at the moment as a sort of potential contender in that space. It does seem to be like hitting a lot of sweet spots there. But anyway, it's not the Zig, it's not the Zig podcast or the Go one for that matter. So the other question that we've probably forgotten, VJ, was like the future.
Yeah, exactly. So I think that's a nice way to round up the podcast. So what is next for you guys? I mean, both on your project and then on your own in your life, and then what are you going to do next after you close this browser window? Very near future and very far future. Feel free to answer only the relevant ones.
Well, so our system is currently in preview. So any customer can go try it if you have an Exoscale account. I mean, you got to put the small commercial in there. But so we're mainly working towards general availability, which means we've got like a few background jobs that we still need to go implement to keep the system efficient. We are looking at designing a custom hardware profile to run the system on. So currently we use the same type of instance or the same type of machine that our storage optimized class of instances run on. And so the idea here was that since we don't know what the system does, or like, because when we needed to order these boxes, we didn't actually have a system. So we chose to order boxes that we could reuse later, basically, and they're a bit overpowered. So we're now kind of taking a look at the monitoring the system, figuring out like how much RAM does it actually need, what kind of performance profile do we want from all of the disks, how much CPU are we using, how many CPUs do we want, these type of things. So we're sort of like, and then we'll design a custom piece of hardware. I mean, custom, like we'll talk with a vendor and try to order a box that fits what we need. It's not like we designed the hardware. And so there's some polishing, and then we want to roll it out to more zones. So like for the product, those are the next few steps. So currently there's one zone. It's scheduled for a second zone before the summer. And then it becomes, I don't know. We need to have some talk with the investors for how many boxes we can buy.
Okay, so I think that's a nice way to round up our adventures of storage land, I think. Thanks a lot, Albin and Aurelien, joining us and explaining. And in a way, I'm very jealous of you guys because all my life I've been just building CRUD applications and shit, and not what they call "quote unquote" real engineering crap. So, so you're doing amazing job. I'm sure. I think as Wouter mentioned, and it's nice that how you're using Clojure. I think we had a few folks from we spoke to some Exoscales people before, and then we were talking about how little bit different Clojure usage is at Exoscale compared to rest of the world, and because you're on the what do you call it, the lower part of the iceberg of the cloud stuff, where the heavy lifting happens, and people just go there, click the button, and then give me RAM, give me buy more RAM, and you're making that happen, and different kind of challenges. So super excited for you guys working on this stuff and having multiple languages to play with and building some solid systems. So and thanks a lot for joining us and sharing all the nitty-gritty details. And I'm sure I learned a lot, and I'm going to build my own block storage system now in OCaml. As you know, I'm an expert now. So
yeah,
it's going to be in French though. So It's a system du storage or whatever the fuck that it's called.
Mirage. Yeah.
It's going to be the other way around. Like it will store before you store.
The unikernel. Yeah.
Exactly.
Yeah.
But I kind of like the fact that Aurelien and Albin are obviously fresh-faced as well, because a lot of Clojure programmers end up, they're sort of
old and grumpy.
Yeah, this is the kind of like, this is the sort of profile of the Clojure programmer. It's a miserable old fart like me,
Exactly,
who's like fed up with the world and like retreats into Lisp essentially as a sort of comfort blanket. So it's nice to see that, you guys are like coming into the industry and you're using Go obviously and things like that, but you're also picking up functional programming and it's good for the future, I think.
Yeah, and thanks, Wouter. Thanks for bringing folks here and giving us an opportunity to talk about all these things. So really appreciate it. I know we had some fun with our podcasting system. Obviously, it's not. I'm sure it's not built in Go or Clojure.
It's not running on Exascale. That was the problem.
Exactly.
No, I really wanted to shine a spotlight on both of these guys, and actually like the extended team, like Miguel, Christian, Pierre Manuel, like and everybody else at Exascale. But like, because funnily enough, like I was listening yesterday and today, I haven't finished yet, to Oxide and Friends, the Brian Cantrell podcast, and they just had an episode out on their block storage system.
Oh, okay.
Where they talk about their design. It took them 4 years to do it. They talk about how a joint they didn't even dare to start because it was too hard. They deemed it was too hard because they and what was, I mean, at least like from my perspective, what was interesting to see was some of the choices they made the same, some of the choices they made different for the same reasons as us. And where like we chose to inherit our blob D layer because we know how to operate it. Like they chose to use ZFS because they wrote ZFS when they were at Sun. So like they made the same decision, but like it ended up turning into a different design, and it was fun to sort of see like how some of the issues they were having are absolute non-issues for us, and the other way around. Like their design like ended up like engineering away some problems that we are facing. So the funny thing about it is that there are not a lot of block storage solutions out there. Like in the open source world, there's essentially Ceph. Also, the cloud vendors have not published papers on how their system works. There is no paper on EBS. There is no paper on how disks work at Azure or at Google. Well, there's a few papers on EBS, but not on the actual thing that matters. Like they've got something around like how the metadata gets replicated.
So there is a few presentations by the guys at Alibaba Cloud that do explain how it's working on their side.
But so in any case, like this is something not a lot of companies have. They're very tight-lipped about it in general. And it's a very performance critical thing. Like if your disk is slow, like your machine is slow. Like it's not. And we managed to, obviously, like there's been like drawings before that, but by and large we did a 2-year effort, and we're shipping something to production now, which I think is record speed. And we're hitting the performance that we wanted, so we're sort of on par with other similar cloud providers like Scaleway or DigitalOcean. Like they offer the same amount of IOPS and the same amount of limitations as we do. So I think all of this is like super nice for what is essentially a V0 or a V1 system. And I don't know, like it for me, it's a really major achievement. And like again, like I wanted to spotlight these guys because I didn't write that much code on this one actually. Like it's really all the team. And
so that is the reason why it was finished in 2 years.
Oh, for sure. Like for sure. I mean, it would have taken a bit longer if it was just. I mean, if I no, but so that's kind of why I pitched it, because I don't know. Like we don't talk that often about how we do things at Exascale, or what we do even, but we I mean, I'm massively biased, but I'm always very proud of what we do, and I think it deserves like a bit more attention. So I thought, like, let's abuse the small little platform I have and shine a spotlight on these guys and what they do.
It's always nice
it's
to
amazing.
understand the other side of it, right? Because I think that's what generates curiosity. That's what generates this. As you mentioned, now people know how this system is built, and they can think about what other problems can we solve with this one. And this is how open thinking and open source and open ideas, go around. And obviously, I mean, for the people who are listening, I mean, there's no way sponsored by Exascale or anything. We don't take sponsorships, but it's more about the engineering knowledge and the kind of problems that we're solving. That it'll be nice to understand the solutions. It'll be nice to understand the trade-offs. It'll be nice to understand how things are built. So it's super nice to have you guys and give us the background details and everything. So thank you guys. Thanks a lot. And I think we would love to have more time, but I think it's almost we're right on time for our brand.
90 minutes.
So thanks a lot. And just before we go, I think I'd like to just give a couple of shout outs for our patrons. I think and there have been people who've been supporting us for a long time now, and there are a few new folks. Alessandro, thank you, and John Sheridan, thanks a lot, and also Schmude. I don't know how to pronounce this in German. It sounds like a German name, but thanks a lot for your support. And if you want to sponsor us, go ahead on our Patreon. And not an obligation, obviously. We love to do this with our friends. We love to do it in our free time, and having wonderful guests. And it's also learning stuff for us and people who are listening. I hope it's also a nice experience for you. Apart from the bullshit that me and Ray produce, but most of the time it's way more quality stuff from the guests. So thanks a lot, guys. Thanks a lot for joining, and thanks a lot for listening. And I think this is the first episode for this year, right?
I don't know.
I think so.
I don't know.
Yeah. In any case, Happy New Year. if this is the first one.
Time's flying.
Exactly. Yeah. Who knows? It might be 2025 when we have the next episode.
All right.
Okay.
Thanks, guys.
Thank you.
Thank you.
Thanks a lot for the invitation.
No worries. Thank you for listening to this episode of Defan. And the awesome vegetarian music or the track is Melon Hamburger by Pizzeri. And the show's audio is mixed by Wouter Dullert. I'm pretty sure I butchered his name. Maybe you should insert your own name here, Dullert.
Wouter.
If you'd like to support us, please do check out our Patreon page, and you can show your appreciation to all the hard work or the lack of hard work that we're doing. And you can also catch up with either Ray, with me, for some unexplainable reason. You want to interact with us, then do check us out on Slack, Clojure and Slack, or Clojureverse, or on Zulip, or just at us at Defan Podcast on Twitter. Enjoy your day, and see you in the next episode.
Fuck! What the hell is this introduction? I thought we were actually gonna be getting better after 94 fucking episodes.